So what if I told you that classifying a movie review as a simple Boolean true or false requires the exact same computational machinery as translating a massive 500-page novel from English to French?
I mean, on the surface, that sounds completely counterintuitive.
Right. Especially if you're sitting there tonight, glowing screen reflecting off your glasses deep in some massive refactoring session. You're a software engineer. You are used to distinct data types, very specific return structs, totally different logic paths for different tasks.
Exactly. You don't use a hammer to turn a screw.
Yeah, but today's deep dive source, it's a piece titled 031 LLM Mastery T5, Treating Everything as Translation. It basically argues that treating every single text-based problem as a literal translation task is, well, it's actually the optimal way to build artificial intelligence.
It really is.
We are unpacking a 2019 paper from Google that introduced a model called T5, which stands for Text-to-Text Transfer Transformer. And for anyone building software right now, this is like the ultimate abstraction.
Oh, absolutely.
It's the story of how an entire sprawling field of specialized machine learning was just ripped out and replaced with a single elegant API. Basically, string goes in, string comes out.
Yeah, and it represents this fundamental paradigm shift in how we structure computational systems.
Yeah.
Because prior to this framework, the machine learning pipeline was incredibly fragmented.
Fragmented how? Like lots of different repos.
Sort of, yeah. Like if your team was assigned to build a sentiment analysis tool, you designed a very specific neural network architecture. And the final layer of that network, what we call the head, it was mathematically engineered to output a probability distribution.
Right.
So it'd spit out a float, like say 0.98, indicating a 98% chance the text was positive.
And if that exact same team was asked to build a translation tool the next day, they couldn't just reuse that architecture.
Not at all. I mean, a translation model doesn't output a single float. It outputs a dynamic, variable length sequence of tokens. The shape of the data is fundamentally different. So you had researchers and engineers maintaining dozens of disparate architectures, custom loss functions, specialized training loops, all separate for summarization, classification, translation, question answering.
It's just a total maintenance nightmare.
Exactly. And T5 just eliminated that entirely. The researchers proposed that if you step back and look at the underlying mechanics, all of these tasks share a universal structure.
Which is what?
You are mapping an input sequence of text to an output sequence of text, period. T5 took that observation and just committed to it entirely. They used the exact same model, exact same objective for every single natural language task.
Okay, let's unpack this for a second. Because if the model architecture is identical for every request, how does the system route the logic?
Right.
Like, how does it know whether I want it to translate a sentence versus summarize a paragraph or, classify a mood?
The mechanism they used is actually beautifully simple. It's task-specific prefixes.
Prefixes, like in the prompt.
Yeah, you literally just prepend a short, hard-coded string of instructions to the front of your input array.
Yeah.
You are feeding the routing logic directly into the context window.
Okay, give me an example.
So if you want sentiment analysis, you pass the model the string, classify. This movie was absolutely brilliant. And instead of the model calculating a numerical probability float, it just generates the literal text string, positive.
Oh, wow. So it's treating the concept of classification as a language translation.
Exactly.
It translates a long, complex English thought into a one-word English category.
Yes. And it scales to incredibly niche academic benchmarks, too. Like the source material highlights this task from the corpus of linguistic acceptability, which is essentially just a grammar check.
Okay.
You feed the model, sentence, the dog walked in the park. The model processes that sequence and outputs the literal string, acceptable.
That is wild. The output mechanism is sequence to sequence across the board.
Across the board.
It's kind of like the universal translator from Star Trek. But instead of translating alien languages, it's translating between abstract computational tasks.
That's a great way to put it.
You're translating a question into an answer, or a sprawling document into a concise summary. But it's the exact same underlying engine computing a different logical destination based on that initial prefix string.
And what's fascinating here is the downstream effect on the engineering workflow. Because there are no different output heads, there's no need to write different training loops.
Oh, right, because everything is just text generation.
Exactly. You are fundamentally training the model on one single unified objective, which is calculate the probability of the next sequence of text based on the previous sequence.
But realizing that unified vision, that forced the researchers to make a very specific architectural choice, right?
It did.
To build this universal translator, they had to decide on the actual shape of the neural network. Which brings us to this big debate between encoder-decoder structures and decoder-only structures.
Right, which is highly relevant today.
Yeah, because we need to look at the broader landscape of AI here. Any engineer integrating an LLM into their app right now is almost certainly using a GPT model. And GPT stands for Generative Pre-trained Transformer. And those models are decoder only. They generate text autoregressively.
Yeah, and autoregressively meaning it operates a lot like a while loop, building an array one element at a time.
Right.
The model looks at the input, predicts the most likely next single token, appends that token to the input string, and then runs the entire newly expanded string back through the network to predict the next token.
It's always moving forward, left to right.
Always.
But T5 deliberately ignored that trend. Instead of going decoder only, they retained the full, bulky encoder-decoder structure from the original 2017 transformer architecture.
They did. And the mathematical reasoning for that choice is crucial for a text-to-text framework. Because in an encoder-decoder setup, the initial input isn't just fed into a forward-moving loop.
Okay, what happens to it?
It is passed into an encoder block that processes the entire sequence bidirectionally.
Bidirectionally.
Yeah, meaning every single word or token in your input prompt can mathematically attend to or basically calculate its relationship with every other token, forward and backward, simultaneously.
So if the input is, say, a complex 10-page legal contract, it's loading the entire context into memory at once, mapping all the dependencies before it ever tries to generate a single word of the summary.
That is the perfect way to visualize it.
Mm-hmm.
The encoder builds this incredibly rich, multi-dimensional matrix representation of the entire prompt. And only after that calculation is fully baked does the decoder component step in.
And then the decoder just writes the output.
Right. The decoder generates the output autoregressively, token by token, just like GPT does. But as it generates each new word, it has this dedicated attention mechanism that constantly cross-references that static, fully formed representation the encoder built.
The source material actually uses an excellent analogy here. It says it's the difference between reading a long, complex letter, digesting its full meaning, thinking about your response, and then sitting down to write your reply, versus reading a letter and trying to compose your reply simultaneously, word by word, as your eyes are literally scanning the page.
Exactly. It's a separation of comprehension and generation.
Putting my software engineer hat on for a second, though, I kind of want to push back on that architecture.
Okay, let's hear it.
Because in system design, we are always optimizing for compute and memory. Why pay the massive computational overhead of having both an encoder block and a decoder block? Like GPT models prove that decoder-only architectures are massively powerful. They generate text beautifully. They're much simpler to scale up across a GPU cluster.
They are.
So why dedicate billions of parameters to an encoder block if a decoder can eventually learn to just read and write at the same time?
It really comes down to separating concerns based on the nature of the task.
Yeah.
If you are building an open-ended chatbot where the goal is just, fluid, creative continuation of a thought, decoder only is incredibly efficient.
Okay.
But the text-to-text framework isn't just chatting. It is dealing with tasks that have a highly complex input and require a highly constrained output, like translating a dense technical manual or summarizing a massive document.
Right.
For those specific transformations, isolating the logic of comprehension from the logic of generation is just mathematically superior. Think of the encoder as a component whose sole computational burden is to study the board, map the pieces, and understand the state of the game.
Like a chess player.
Exactly.
Yeah.
And the decoder is the component calculating the next move. Forcing one network to do both simultaneously, it dilutes the model's capacity to build deep contextual relationships in the source text.
Okay, that actually makes a lot of sense. So you are basically allocating a massive chunk of your compute budget exclusively for reading comprehension.
Yes.
Which is perfect if your primary goal is translation or summarization.
Mm-hmm.
But, an architecture, no matter how elegant, is just uncompiled code without data to train it on.
Oh, absolutely.
If they built this incredible engine to perform universal translation, they needed an unprecedented amount of fuel to teach it how human language actually works.
They needed a data set that matched the ambition of the architecture. And this is where the T5 team introduced T4, which stands for the Colossal Clean-Crawled Corpus.
The raw material for C4 came from Common Crawl, right? Which, for those unfamiliar, is essentially a massive ongoing scraping of the entire public internet. It is an astronomical amount of
It's
text.
huge, but it is also highly unstructured and filled with garbage. I mean, if you just train a model on raw Common Crawl, you are feeding it boilerplate HTML menus, SEO keyword stuffing, spam advertisements, broken code snippets.
Basically the worst parts of the web.
Yeah, and highly toxic content too. And a model learns the distribution of its training data. If you feed it noise, it will generate noise. So the T5 researchers engineered this incredibly aggressive data pipeline to filter this raw scrape.
And they didn't just throw standard, regular expressions at it, right? They instituted strict programmatic heuristics to distill the internet down to high-quality natural language.
Yeah, the specific filters they applied are fascinating from a data engineering perspective because they didn't just look for bad words, they looked for the structural indicators of bad text.
Give me an example of a structural indicator.
So they started by dropping any page that contained words from a comprehensive offensive block list. Standard stuff. But then they looked at the structure of the text itself. They stripped out any line that didn't end in proper terminal punctuation.
Meaning a period, an exclamation mark, or a question mark.
Exactly.
Just thinking about the rejects for that single rule would instantly wipe out millions of lines of navigation bars, footer links, drop-down menus, fragmented HTML tags.
Gone. Instantly.
You are forcing the dataset to only include complete, deliberate thoughts.
It fundamentally shifts the quality of the tokens. And they also drop pages that contained very few sentences overall, assuming they lacked meaningful context.
Makes sense.
They ran aggressive hashing algorithms to deduplicate pages across the entire corpus.
Oh, that's critical. Because if a model sees the same spam message or like a software license agreement repeated 1,000 times, it'll memorize it. It'll over-index on that pattern.
Exactly. And finally, they passed the remaining text through a language identification model to ensure the dataset was strictly English.
So they piped this massive ocean of raw internet data through a gauntlet of structural filters. And what came out the other side was about 750 gigabytes of pure, high-quality, grammatically structured English.
Pure signal.
It proves a vital principle in machine learning, honestly. You cannot simply throw more GPU compute at bad data and expect intelligence to emerge. Garbage in, garbage out. The data pipeline is the product.
It really is. And the careful curation of C4 became a benchmark for the industry. But, once you have that pristine data set, you still have to design the actual training loop.
Right. How do you pass 750 gigabytes of text into the model and force it to learn the underlying rules of language?
Exactly. And this brings us to T5's unique pre-training objective.
And here's where it gets really interesting, I think, because they didn't use the standard approaches at all. Like in a GPT model, the training objective is simple next token prediction. It reads the quick brown and tries to predict fox.
Right.
In a BERT model, the objective is masked language modeling. It takes the quick brown fox, hides the word brown, and forces the model to guess that single missing word based on the surrounding context. But T5 does something entirely different called span corruption.
Yeah, span corruption is a much more complex computational puzzle. Instead of masking a single token, the pre-processing algorithm randomly selects contiguous spans of text.
Meaning chunks of multiple consecutive words.
Exactly. And it replaces that entire span with a single unique variable marker known as a sentinel token.
Okay, let's map this out with the classic example from the source material. Imagine the training string is, the quick brown fox jumps over the lazy dog. The T5 data pipeline processes the string and decides to corrupt two different spans. It rips out the phrase brown fox and replaces it with marker X. Then it rips out the phrase the lazy and replaces it with marker Y.
Right.
So the input array passed to the encoder is literally the quick marker X jumps over marker Y dog.
Yep. And the encoder processes that corrupted string, builds its matrix representation, and passes it to the decoder. Now, the decoder's target output, the exact string it must generate to minimize its loss function, is just the missing pieces.
Not the whole sentence.
No, just the pieces. It needs to output marker X brown fox, marker Y the lazy. It is essentially solving a multi-word fill-in-blank puzzle.
But wait, if they corrupt a whole multi-words span, the model can't just rely on local statistical variables. Like if you only mask the word fox, the model sees brown right before it and jumps right after it. Fox is a highly probable statistical fit just based on local proximity. But if you blank out brown fox entirely, The model has to load the logic of the entire sentence into memory to deduce what belongs there. It has to understand the grammar and the physics of the scene. Is that why span corruption forces deeper semantic reasoning?
That is the exact mathematical advantage. You are removing the local crutches. By forcing the model to predict a sequence of missing words, you force it to map long-range dependencies.
Wow.
It has to understand that whatever goes into marker X must be a noun phrase capable of jumping over whatever goes into marker Y. It moves the learning process from simple vocabulary memorization to true syntactic and semantic comprehension.
And there has to be a huge efficiency gain here too, right? If you were generating a target sequence that only contains the missing words, rather than forcing the model to reconstruct the entire, say, 1,000-word document just to fix a few blanks, you're saving a massive amount of compute during the backpropagation phase.
Oh, the computational savings are massive. By corrupting spans, they are only actually altering and calculating loss on about 15% of the original text.
It's incredible.
Yeah, the target sequence the decoder has to generate is incredibly short. This means the matrices involved in calculating the gradients are much smaller, which makes the pre-training process significantly faster and cheaper than objectives that require regenerating the full input from scratch.
So, okay, the researchers have this elegant text-to-text theory. They have the bidirectional encoder-decoder architecture. They have the pristine C4 data set. And they have this highly efficient span corruption training loop.
Yep, all the pieces.
But in software engineering, a theory is completely useless without unit tests. How did they actually prove mathematically that this specific configuration was optimal?
They proved it through one of the most exhaustive ablation studies ever published in machine learning.
An ablation study.
Yeah, it's basically the scientific method applied to neural networks. You hold the entire system constant, and you systematically remove or alter one single variable at a time to isolate its specific impact on performance.
It is the equivalent of A/B testing microservices in a massive distributed system. You deploy 50 different routing configurations, monitor the latency and error rates of each, and empirically determine the optimal setup.
Exactly. The T5 team didn't just train one model. They trained dozens and dozens of variations.
Like a master chef baking 50 slightly different cakes to find the perfect recipe.
Pretty much. They tested every core assumption of their architecture. For example, we discussed why encoder-decoder makes sense conceptually, but they actually tested it against decoder-only models and against something called a prefix language model.
A prefix language model is basically a hybrid, right? It's a decoder-only architecture,
Right.
but it modifies the attention mask so that the model can look at the entire prefix prompt bidirectionally, but then generates the output autoregressively.
Exactly that. It attempts to get the best of both worlds without the parameter overhead of a separate encoder block.
Right.
But the ablation study proved that the strict parameter separation of a dedicated encoder and a dedicated decoder consistently achieved higher scores on complex language benchmarks.
Interesting.
They also systematically tested pre-training objectives. They ran parallel training runs comparing standard left-to-right generation, BERT-style single-word masking, and various rates of span corruption.
And span corruption won?
Yeah. The empirical data showed span corruption with a 15% corruption rate was the optimal balance of performance and compute efficiency.
They even tested data mixing strategies, right? Because when you have a model that needs to be pre-trained on the massive C4 dataset to learn general language, but then fine-tuned on specific datasets for translation or summarization, how do you handle that pipeline?
Right. Do you pre-train sequentially and then fine-tune?
Hmm.
Or do you mix all the data together from the very beginning?
What did they find?
They found that standard sequential pre-training on C4 and then fine-tuning on downstream tasks was generally the most effective. But they mapped out the exact degradation curves if you chose to mix the data. They essentially created an empirical map of the entire language model design space. They logged the exact interplay between model parameter count, training duration, and dataset size.
You know, the value of that empirical map to the broader engineering community cannot be overstated. Google spent millions of dollars in compute cluster time to run all of these dead-end experiments and suboptimal configurations so that nobody else had to.
Yep.
They essentially published the ultimate mathematically verified configuration file for training large language models.
It democratized a huge amount of foundational knowledge. And they paired that research with open access to the models themselves. They didn't just lock the final optimized model behind a private API.
Right. They released the weights for an entire spectrum of T5 models, which proved a critical concept about scaling laws.
Yes. They released everything from T5 small, which had about 60 million parameters and could easily be run locally on a standard GPU by a grad student,
Love that.
all the way up to T511B, an 11 billion parameter model that required heavy enterprise hardware but achieved state-of-the-art results across the board.
By releasing that spectrum, they prove that intelligence and capability in these models scale predictably with compute. Like the underlying code, the architecture, the text-to-text framework of T5 small are mathematically identical to T511B.
Identical.
The only variables that change are the depth of the layers and the dimensionality of the hidden states. It proved that size is just a lever you pull based on your compute budget. The architecture scales flawlessly from a laptop to a supercomputer.
It's just an incredible piece of engineering.
But as powerful as that original T5 model was, interacting with it was still highly rigid, wasn't it? Prepending exact strings like sentence to your input feels like writing bash scripts or terminal commands.
It does. It's brittle.
Yeah. If you make a typo in the prefix, the routing logic fails. So how did the industry move from that rigid, prefix-driven architecture to the fluid, dynamic conversational interfaces we interact with today?
That evolution was driven by a subsequent iteration of the model called FLAN T5.
Flan! Like the dessert.
It's spelled the same, but it stands for Fine-Tuned Language Net. It took the brilliant text-to-text foundation of T5 and applied a technique called instruction tuning.
Instruction tuning. Okay.
The researchers realized that relying on hard-coded prefixes limited the model's ability to generalize. So they gathered thousands of diverse NLP tasks and phrased them not as programmatic prefixes, but as natural, human-readable instructions.
Oh, I see. So instead of passing the array, translate English to French, the network is down, you would pass it a conversational prompt like, could you please translate the following error message from English into French?
Precisely. The model wasn't just learning to pattern match a specific string with a colon. It was learning the underlying semantic intent of the instruction itself.
That's a huge leap.
It is.
Yeah.
By training the model to follow instructions across thousands of different task types, FLAN T5 developed an emergent ability to zero-shot generalize. It learned how to follow instructions for tasks it had never explicitly seen during training, simply because it understood the structure of an instruction.
If we connect this to the bigger picture, that instruction tuning phase is the exact technical foundation of modern prompt engineering.
Yes. Okay.
When an engineer today sits down with an API for ChatGPT or Claude or Gemini and writes a system prompt saying, you are a code reviewer, read this Python script, find any memory leaks, and output the corrected code in a markdown block, they are relying entirely on the instruction-following capabilities pioneered by the FLAN T5 architecture.
The shift from custom output heads to a unified text-to-text framework didn't just simplify training, it fundamentally changed how humans interface with AI. By insisting that the output space must be identical to the input space, that both must be raw strings of natural language, T5 made model outputs inherently readable, debuggable, and most importantly, chainable.
That chainability is everything in modern software architecture. If function A returns a string and function B takes a string as an input, you can pipe them together infinitely. You can deploy an ecosystem of microagents where Agent 1 summarizes a Jira ticket, passes that string to Agent 2, which translates it to German, and passes that string to Agent 3, which generates a code snippet based on the translation. The text-to-text framework is the foundational logic of the AI agent architectures exploding in the industry right now.
The premise that every problem can be treated as a translation task wasn't just an academic trick. It was the architectural prerequisite for the entire chat-based, agent-driven era of artificial intelligence.
So what does this all mean for you, the engineer staring at your IDE right now? We started by looking at a hypothetical, sprawling code base full of highly specialized disparate functions, and we asked if it was possible to refactor the entire thing into a single, elegant, string-in, string-out API.
And T5 proved that not only is it possible, but it is actually mathematically superior.
Yeah. By combining strict architectural separation of concerns, ruthlessly filtered data pipelines, computationally efficient training loops like span corruption, and an obsessive commitment to empirical ablation testing, Google unified the entire field of natural language processing under one roof.
It proves that the way we frame a computational problem defines the limits of our solution. Framing everything as a sequence-to-sequence translation completely unlock the latent potential of transformer networks.
Which leaves us with one final kind of mind-bending architectural thought to mull over. The entire T5 philosophy rests on the proven idea that any text-based problem can be treated as a translation problem. String in, string out. But what happens if you expand the definition of a string?
Oh, man.
What happens when you leave text entirely?
That is exactly where the frontier of machine learning went next.
What if you take a photograph, a high-resolution image, and you literally slice it up into a grid of 16 by 16 pixel patches? What if you flatten those visual patches into an array and pass them into a transformer architecture exactly the same way T5 processes a string of words?
It's wild to think about.
Could an image just be another language, another sequence of tokens waiting to be translated? That is the underlying logic of vision transformers, and the math behind it will completely break your brain. But for now, take a sip of that coffee, get back to your refactoring session, and remember, if you zoom out far enough, every function is just translation. Keep tinkering, keep building, and we'll see you on the next deep dive.